This video is going to introduce you to the major phenomena of degradation that must be taken into account for component selection in mechatronic systems. The evaluation models must permit to evaluate the capacity of a component to function safely over its whole lifetime as required on its specifications. And of course, this must cover all design scenarios. Evaluation models must ensure that the components we've selected can satisfy transient power demands. In that case, we will talk about performances, and we will make sure, for instance, that maximum torque or speed of a component are never exceeded. The objective is to avoid any sudden deterioration of a component. Continuous or repetitive power demands. In that case, we will talk about endurance or durability, and we will make sure that the fatigue torque or speed don't exceed acceptable limits. Here, the objective is to determine a certain lifetime in case of progressive degradations. Mechanic loads to displace by the dispositive we conceive can be characterized by certain notions, such as displacement, rest time, speed, power, and energy. Operational limits in transient domain can be represented by a power plan like the effort speed one. These effort speed characteristics, or effort position, allow us to represent, in a graphic way, the principal mechanic attributes of an actuator, effort, speed, and, as a product of those, power. Isopower curves, curves along which the power remains constant, have an hyperbolic form, or a linear one in a logarithmic scale in the case of effort and speed. This effort speed plan in mechanics, voltage current in electrics, pressure flow in hydraulics, can represent, in an averaged way, the operational limits of a component. Those graphs show the operational limits in an effort speed plan for several components. 1. A mechanic reducer, gears. 2. A combustion motor. 3. An hydraulic jack, piloted by a servo. 4. An electric motor, with permanent magnets and a speed variator. We can also use this graphic representation to characterize mechanic loads to displace with the receiver conventions. 1. For constant torque, lifting devices, conveyors, high-speed vehicles. 2. Torques proportional to the speed to the power. 2. Fans, pumps, propellers. 3. Constant speed, synchronous alternators. 4. Constant power, winding devices, lathe machines. And 5. Any emission profile which varies with time. Lifetime of a component depends on its working conditions, such as the effort on bearings, or the temperature of windings. It can be expressed in a number of rotations, number of solicitations, duration, and many more. It is defined in a statistic way for a certain failure rate. It is often 10% of failure, or 90% of components without any issue. We will not discuss here the failure rate distribution. For mechanical components, the repetition of deformations can create micro cracks in the materials and reduces their robustness to stress and plastic deformations. We call this phenomenon the fatigue. Bearings, components that are mainly responsible for the transmission of mechanical powers, have been studied really precisely regarding this. Rotation tests under certain loads have demonstrated the relation between lifetime and effort. This relation has a linear form on a logarithmic scale, thus can be expressed under a power relation, called rule of Minor-Palmgren. The power of 3, or 1/3, is really typical of bearings. Electrical motors have a high percentage of failure due to mechanical bearings failure. However, we mustn't forget some failures exist because of thermal deterioration of windings. Excessive temperatures often diminish the lifespan of isolating materials and increases the short circuit risk or electrical breakdowns. The relation between lifetime and temperature is expressed by a law that we call Arrhenius type. Constructors often give coefficients for these relations and classify isolators based on their working temperature for a lifespan of 20,000 hours. In the power electronics domain, power modules, such as MOSFET or IGBT transistors, are composed by silicon, isolators, electrical conductors with varying thermal dilatation coefficients. As a result, the thermal cycling implies mechanical constraint variations and the thermal mechanical fatigue. Rupture can occur on the ship's brace joints or around boundings. The aging laws, like Coffing-Manton ones, link the number of cycles before rupture to the amplitude of the temperature variations. Batteries have a really limited lifetime, and in particular, a limited number of discharge cycles. The number of cycles depend on the amplitude of discharge. The relation between the depth of discharge and the number of cycles can be represented under a power law form, as you can see here. The following table shows the different mechanisms of deterioration we can encounter for mechatronic systems, such as mechanical fatigue, thermal degradation, thermal mechanical one, and the depth of discharge.